Okay, so we carry on to the next speaker. This is Gunther Schreier from DLR in Oberpfaffenhofen. He is head of business development of the German Remote Sensing Data Center, and he is coordinating the GMES-related programs within DLR. He has served in various functions, and he's doing technology transfer in a team established between ESA and DLR called Processing and Archiving Center. He has contributed to Earth observation standards and data policy and worked with several international groups. He will present us a paper on disaster help from space, which will include very timely data which also relate to the recent disaster in Haiti. Gunther, please go ahead.
Thank you, Mr. Chairman. Dear audience, distinguished guests, I have the honor and it's a pleasure for me to be here and being invited to give a presentation on some technology, some thoughts of my own, some new innovations, and some pictures finally on how space technology can help people who are endangered by natural disasters, how space technology, namely Earth observation, can help to supply information for rescue teams, for aid teams, NGOs and national organizations. Let's see how this works. Yeah. Now the previous speaker, who unfortunately left already, has given us a brief introduction to the marvelous engineering and technology achievements of manned spaceflight. How to build, how to sustain, how to operate the International Space Station. I think it's the largest man-habited outside the atmosphere. However, still the largest habitat we all live is underneath the atmosphere, is our Earth. And we have developed also space technologies to look from outer space through the atmosphere down to Earth. Some of these technologies, some active technologies, like here radar technologies, might even be used to look at the other smaller habitat, the artificial habitat. So this is a radar image taken from the TerraSAR-X mission in March 2008. So this is a radar image of the ISS space station. It was done with the TerraSAR-X satellite, a DLR, public-private partnership satellite, and this carries a specific technology, so-called synthetic aperture radar, in short SAR. What it does, it emits active radar pulses, receives the radar pulses reflected from Earth, and samples this coherent radiation on a synthetic aperture array during its path around the Earth, and creates with sophisticated computing technology out of the holographic information an image visible to the naked eye and being interpretable by human interpreters, such as this image of Sydney, taken over Sydney. In fact, this is a TerraSAR-X image taken at 3 different dates. And thanks to the SAR imaging physics and thanks to the very precise parameters of TerraSAR-X, we can put each time on top of each other, giving it a color. So what it does mean that if there is no change at all, it just looks black and white. And if you have a temporal change in one of the 3 images, it looks colored. You see, for instance, the greenish ghost ship, which was just a tour ship, which was there at one date and not at the others. And you might notice also the bluish and reddish container terminals. We just show the go and come of containers being shipped there to the harbors. But however, this is just giving a change of the landscape of being there or not being there, or a change in the domain of few meters. Radar technology and microwaves carry lots of more possibilities, named SAR interferometry. You're able to measure fractions of a change in a fraction of the wavelengths of the radar in space. With the X-band radar, which means you have about 3 centimeters wavelengths, you measure fractions of change of a few millimeters. If you even measure then the difference of these fractions, you end up with differential interferometry, So how much has something changed? And we have done this, as many others have done this with radars. Nearly all new radars can do this in space. Is to measure, for instance, the change here of the Tokyo skyscrapers due to thermal movement or due to wind. Now, if you can measure skyscrapers' movement, can we measure the surface of the Earth? Yes, you can. And in fact, radar technology, SAR interferometry, is used around the globe to look into seismic areas to estimate what's happening on ground. Has different caveats to do this, but this is a picture, for instance, of the Stromboli volcano, also an interferogram. And what you see here, these colored areas are so-called fringes, is basically the 2 pi wavelengths of the up and down of the volcano due to the magma underneath. What you can do with volcanoes, you can possibly do also with earthquakes. Unfortunately, unlike to volcanoes, where you might even be able to predict if something is going up very rapidly, that something is going to happen very soon, earthquakes are less predictable. But what you can use SAR interferometry to look what has happened to the ground, what was the mechanism, the physical mechanism of the earthquake with radar interferometry. This is a very early interferogram with ERS Envisat done after the devastating earthquake in Iran in Bam. So you see how the mechanism of the earthquake and the fault has passed through to the surface of the Earth. Radar is good for penetrating clouds. Radar is active during day and night active, and the radar wavelengths is not so sensitive as optical wavelengths to roughness. So what seems to be very rough in an optical image seems to be very smooth and looks like a mirror in a radar image. So radar is good to look to very smooth surfaces on an otherwise troubled ocean surface, troubled by wind and waves. So radar is good to measure, for instance, oil slicks, to detect oil slicks, because the oil is tempting to damp a little bit the surface waves, which you can't see with the naked eyes, but for radar it acts like a reflector, like a mirror. So oil slicks appear to be dark in radar image, such as this oil slick here at the Kerch Street as a tanker disaster in the Black Sea area. So oil slicks are measured with radar technology, with radar spaceborne technology all around the globe. Oil slicks either deliberately exposed by ships or caused by these kind of accidents like this tanker accident in the Kerch Street. Water also acts as a kind of reflecting mirror for radar waves. So water mostly appears also, if it's calm, black in radar imagery. So this is always good if you say, if I like to detect water, and I like to detect water where it has not been before, radar is good for measuring the extent of floods. So this, for instance, here measuring with radar technology and radar imaging the extent of floods in Myanmar after a devastating cyclone. And this kind of analysis is good to access for the research teams, for the rescue teams in field. Is this road still drivable to get there? Or do I need a boat, or in best case or worst cases, even a helicopter to get my supplies or to rescue people? So this is good for radar, and this is where radar is good for, because this also works, see floods, see cyclones during clouds. We come back to these kind of radar data later. Let's focus a little bit on the other range of possible emergencies of personal natural disasters which can be observed from space. Fires. Pretty easy to detect if it's not clouded. Cloud plumes can be detected by fairly medium resolution optical images which are now circling the Earth and imaging large landscapes of the Earth several times per day. Using even infrared images, you might even be able to look a little bit closer to the fire, to the extent, the range of the fire, and even estimate possibly what caused the fire. Is it just grassland, is it wood, or is it an artificial oil fire, for instance? Using higher resolution optical images in the metric or few metric domains. These multispectral fingerprints allow us also to access in a little bit more detail which area was burned after a fire, what is the extent of the fire, and which was not affected as a fire. This is good for rebuild and reconstruction, but this is also of interest for insurance companies, for instance, to estimate, is it a right or a false claim which was made? Was my ground affected by fire, or was it not? In fact, insurance companies are interested in this kind of information, and natural disasters, of course, apart from all these human catastrophes, is also a big issue of economy. Imagine Haiti rebuilding or even building in the first place. The economy is a big financial issue. Insurance is a big financial issue, and reinsurance is an even bigger financial issue. So the large reinsurance companies are very eager to keep track what's ongoing on the world with regard to disasters, to see what kind of transactions they have to do and where risk and chances all over the earth are spread. A very big risk and two big risks are in fact very closely linked to each other: earthquakes and tsunamis. I will later come back to this area of tsunami. And in fact, what tsunami and earthquake have together, they are not new tsunamis, they are old, but only since a few years, since 10 or 15 years, we have this space-based means to measure the extent and the effect of earthquakes and tsunamis caused to our environment and to habitats of mankind. This is an image before the dangerous tsunami in December 2004, which hit the Indonesian coast. Well, this was a time when, 2004, we had the first higher resolution images in space, most of them US commercial companies available. This was a time where DLR and other teams and research groups in the world formed together and got together to estimate what can be done with Earth observation from space to access damage, to assess disasters. So this kind of change visible from outer space, visible with high resolution image, was also a brutal reality check for us. What can be done with Earth observation and space observation, and where are still big challenges, technology and intellectual challenges ahead of us. Now, apart from these changes before and after what was damaged by a tsunami, can we help more? Can we even prevent disasters? Can we save lives by alerting people? Now, after this tsunami, the German and the Indonesian government decided to build up a tsunami early warning system in the Indian Ocean. Though the tsunami waves on the open ocean speeds like a jet airplane, 800, 900 kilometers per hour, but in the open ocean it gives enough alert warning time, a few minutes, a dozens of minutes, to alert people. And using seismics, using tide gauges on the open ocean, using models to estimate what happens if there is an earthquake, how would the land be affected, you have enough time possibly to warn the people to get away from the shores and to save ground. Now, this is a system which is now installed, and DLR specifically was involved in the situation and decision support system, and to a large extent space technology has been used, both space communication technologies, GPS navigation technologies, and to a large extent Earth observation technologies, especially in the decision support system. And since late last year, the system is now operational in Indonesia and Jakarta, and since even then has undergone practical tests, practical alerts, warnings which have been issued, but also issues which says there was an earthquake, but there's possibly no tsunami to come. This is also an important message. If you think tsunami is an exotic threat which comes somehow out of Southeast Asia, remind what happened to Chile, which was also devastated by a tsunami then on coast, and have a look to this slide of historical tsunamis up to now. And in fact, the Mediterranean is likewise prone to tsunamis. The biblical flood might be a tsunami. The Minoan culture might have been deleted, might have been wasted from the face of the earth by a tsunami, giving a rise of the myth of Atlantis. And the challenge here in the Mediterranean is, of course, the very low distances. It's not far away from the coast, so the warning time is very, very short in the Mediterranean. It's challenging. You need lots of satellite system, you need lots of Earth observation and other systems to assess a warning, to give an alert, and possibly to assess what happens to disasters. Now, this kind of getting together Earth observation system is now focused in Europe, what is called the GMES program, the Global Monitoring of Earth and Environment. It's in the European Space Strategy, the second pillar next to the Galileo, the satellite navigation system. And GMES is driven by national, European national partners, national and even commercial Earth observation systems, but also driven by a dedicated fleet of EU and ESA-built satellite called the Sentinels, which are aimed to support global and European applications. Applications which have been identified and which range from urban mapping to land and ecology mapping to marine observation, security, atmosphere and climate change, and emergency mapping. Rapid mapping for disasters is one of the key and core issues in this GMES program. Rapid response for disasters. And the European Commission has set up, together with ESA, a series of big projects to implement now the core and pre-operational phases of all these applications within GMES. The project installed for emergency mapping, for rapid mapping in case of natural disasters, is called SAFER. It's a big project which unifies about 54 international partners, and it's addressing and already now doing practical rapid mapping and assessment maps using satellite data and other informations around the globe. It's also setting up the operational chain from the alerting of a disaster, who tells whom that a disaster has struck, and who tells that there is an alert and you have to act. So it's international coordination. It's moreover international coordination between the experts in this field and the space and ground segment, the mission operators, to make happen that satellites are tasked there in time. It's also using archive data, as you have seen, flood before, earthquake before and after. You need to also have a reference image before the disaster has struck, just to compare. And it's coordinating the experts who customize their expertise according to the kind of data, radar, optical, the kind of disaster, flood, earthquake, and the kind of user in field. What's crucial for these entire systems is has to be very, very fast. The goal here set by the experts, European experts in this team, is give me an assessment map, give me a rapid assessment, a detailed assessment what happened 24 hours after the disaster. So you need to act very, very fast. Unfortunately, Earth observation missions are not stable over one ground, unlike weather satellites, for instance. They're not geostationary, but they circle the globe around the poles. So in order to have frequent contact with these kinds of Earth observation missions, you need to have good positioned stations, and DLR, like others, have now built up a series of stations near polar areas, just to be able to command satellites more often, to get data from these satellites more often. And we have recently updated, for instance, together with Canada, established with Canada and other partners in Europe, a new polar station in Inuvik in northwest Canada. But if you really like to go to near real-time, to real-time access to satellite, you need to think of other technologies. One such technology is, first of all, to ensure that you have a safe communication link between satellite and ground. One of these communication links and technologies is laser technology, laser communication terminal technologies, which will be supported by the first two Sentinels. Sentinel 1 and 2 will have this laser communication technology. That's good, but you need to have a communication tower in space. You need to have relay satellites, as I think US has for the ISS mission. as Japan has and Europe has for Earth observation missions. And in the time of GMES, the plan is for Europe to have at least 3 of these communication towers, European data relay satellites in space. Most of them are equipped with the technology of laser communication, so to enable all around the globe communication with the satellite. The good thing, it's not only good for Sentinel, but any other, even other nations' Earth observation satellite, which is adequately equipped with these kind of technology, can use this EDRS system in order to respond to emergencies and other threats. Emergencies and threats which happen, for instance, in Haiti. This is a QuickBird high-resolution image of the center of Port-au-Prince with the roof of the cathedral gone and the other buildings around the cathedral damaged. Now this is an interesting or a horrifying image, so to say, to look at, and it's nice for the press, but what the emergency aid troops, what first responders really need is more an overview image in like 1 to 25 to 5,000. Where are the areas in the city which are most destroyed? Where do I have to focus my relief on? So what has been agreed with internationally is to have this kind of maps colored where are most damaged areas in the cities, and this is just a zoom in into this. So this is what is needed, what is delivered in time, within hours, within days, to the support teams in field, to give them an introduction and to give them an overview where to go to. Another overview is, once again, this interferometric image of analysis of the earthquake in Haiti, once again done with TerraSAX. So my colleagues estimated from this interferometric measurement that the red area in the west here of Port-au-Prince was about shifted 1.3 meters to the west due to this earthquake. Now luckily we had in our archives a TerraSAX image pre-earthquake, because if you have no pre-earthquake, how you can determine how much the earth has moved. So the concept is, how can we make sure that seismic endangered zones are covered with radar imagery? And the Group on Earth Observation, has issued a concept which is called supersites on geologically active regions. So they have defined some known supersites. Interestingly enough, Tokyo, Los Angeles are amongst these supersites, where mission operators of radar say, I take always an image here, and they have added also some new event supersites like the Chile. And from this webpage I just took a few other examples, like displacements here on the Chile earthquake as measured with the Japanese ALOS PALSA satellite, likewise. But also other measurements, non-imaging technologies like GPS, can be used to measure the large displacements which have been caused by the earthquake. This is a reference measurement from the Concepcion station, a GPS reference station, and it said that the city of Concepcion just moved 3 meters from its original place where it has been on the surface of the earth due to the earthquake in Haiti, in Chile, sorry. Now, while this kind of supersite concept is more an academic approach and geophysical approach to understand earthquake mechanisms, and is also more a challenging issue for the radar engineers to squeeze even more out of radar data, there is another organization which is now in place since 10 years, which really aims to support civil protection and relief organizations, both on national and international arena, with real data. This is the Charter on Space and Major Disasters. It's a group of agencies which says, let's put together, let's target our satellites which we have in our portfolio, and to image areas which are hit by disasters and give the data to those for free which need this data to analyze this disaster. I think that's fine, and the Charter has gained 10 years of experience, and the concept of disaster managing and images for disaster from space has made it as a core to GMES. But I think we need also have a more stringent charter. The Charter is a voluntary club. You may or may not deliver. I think we need a more binding agreement amongst the spacefaring nations and agencies that there is an obligation that you have to deliver image in case somebody is in need for this image due to a natural disasters. I think what I try to show you is that we need to use space technology, and we have to use space technology to save our habitat, our Earth, for the sake of our benefit, but also for the sake of the benefit of the generations to come. Thank you very much.